We're good to start?
Yes. Hi, everyone. Welcome to Quantum Conversations number 8. I'm Mert. If you are seeing me for the first time, I started working with Alexei on Quantum Conversations when I was at Stanford. Now I graduated and manage the site together with Stanford Quantum Computing Association. So Yosh is leading the partnerships at Stanford now. We'll be hosting researchers from Sigmoid today. Sigmoid is a data solutions company. They build and manage the largest data platforms in the world. They're also looking into quantum technologies. It was actually their blog post on quantum support vector machines that made us reach out to them. So today we will be talking about quantum machine learning. And so usually we ask everyone to introduce themselves. So we'll go ahead and do that now. We'll do a quick intro, name, affiliation. So affiliation, I mean like school or company, and what they're interested in quantum. So maybe let's start with Alexei and then go on to Sigmoid researchers, if that's fine.
Awesome. Thank you, Mert. Yeah, really excited for this partnership. As you know, I joined IBM. I was a community partner, right, working outside IBM for years, and finally kind of jumped in. And obviously, this meeting space is neutral and third party, so I didn't want to make it kind of IBM thing, and so it's very appropriate, right? I needed to hand it off to community folks in terms of running it actually, and so Stanford Quantum stepped up and Mert graciously agreed to drive it. So really excited for that, because I think Mert is the example of people we need to make more of during this process, right? Like learn about it, go to industry, do it, right, to teach new people. And so Mert already shared a bunch of learning resources and contributed a bunch of insights. And I think this is the main purpose of this. How do we learn this? And I just started the job, right? Like we've been about a month, and like I feel like I know much less now, right? Like because there's so much stuff. Like the more I go into it, like the less I know. So it never ends. We have a bunch of a mix here. So just gonna be helping from kind of community side, right? And super excited, that like there is a team now kind of leading this forward, and we will supporting. I will kind of represent IBM. I will be supporting quantum conversations, but it doesn't mean like we're open for everything. Like it's very important to understand. I'm not the voice of IBM in the sense that I don't represent IBM officially. I represent the idea that community is important. That's it. So thank you guys. Looking forward.
Perfect. Thanks, Alexei. So Ashish, can you introduce yourself, please?
Sure. Thank you. First of all, thank you very much for calling us in and having us part of the quantum conversations. I would say it was very opportune wherein we got a message from Alexei. We were able to find some fan/following on a blog that we wrote some time back. It was a long time back, but we'll talk about that later in these conversations as well. Quickly talking about myself, I am an IIT-Kanpur pass out. It's an engineering technology institute in India. I did my mathematics and scientific computing masters from there, passed in the year 2007. Since then, have been working in the analytics and data science industry, sometimes in the services industry, some part in the AI and healthcare product companies as well. Currently, I work as the head of data science in the vice president position at Sigmoid Analytics. At Sigmoid Analytics, I think you already mentioned, but we provide data solutions which encompass data engineering, data sciences, and as part of our job, not the regular part of our day job, we do some research and R&D as well. One part of that is some research on quantum computing. Just to give you some context on where it started, I did my summer internship in University of Mathematics, India in France. It was a 3-month course which I did under Professor Dimitri Petritis. And therein we religiously used to follow Julia Kemp, who was from University of Paris in France at IBM again, and she had done huge amount of research in that at that point of time in 2005 on quantum random walks, and that was my research topic as well, which I did I think 15 years back. I barely remember a large part of it, but that is where the curiosity into quantum computing area began, and we did put in some efforts at Sigmoid Analytics to build at least some part of our knowledge in that particular area. We're able to write some application based uh, blogs, which we'll talk about soon. And those blogs are more oriented towards utilizing qiskit library for practical applications, including some analysis that we were able to perform on breast cancer data as well. So that being said, I would put a caution. I would probably start with low expectations. So we are not full-fledged researchers. This is something that we do out of our interest, and as much as time that we can gather, uh, we are no more than rookies or novices. Very much enthusiasts into quantum computing, but no way experts. So please feel free to shoot questions to us. We might be able to answer few of them during these conversations, or we'll certainly note them down for being able to address in future. Uh, with me, I have four of my colleagues as well. We would probably ask them to introduce as well. We'll probably start with Jayant. Jayant, would you? So can I do that? What? I'll
Yeah,
ask
go
my team.
ahead. This is a free
Sure.
for all.
All right, great. Jayant, introductions from your side, please.
Yeah, sure. Thanks, Ashish. So I had the marketing at Sigmoid, and I specialize in B2B marketing and have been helping technology companies in building their brand visibility as well as creating demand. And I'm really pleased to be participating in this conversation today. Thank you.
Thanks, Jayant. And I think we have
That's right.
Bhaskar.
Bhaskar.
Yeah.
Yes.
Yeah, thank you, Matt. So, hi everyone, Bhaskar here. So, I am a senior data scientist at Sigmoid currently. So, and I have around 8 years of experience in this analytics and the data science domain. So that's pretty much about the professional side of me. But coming back to the research part, as Ashish was mentioning, um, so it's a great opportunity for us at Sigmoid to research on something very cool actually. So this is something which I've never expected, which I would be doing. So it's like as Ashish mentioned, so his research from 15 years ago inspired or directed us to start researching on quantum computing as one of the research topics. Like we were also researching on a couple more topics, but like this is something which we as a group like we were doing. So myself, Amit and Anirudh, and like we could actually like get into really cool things and practical implications of something which is very futuristic and everything. So that was great about this particular research activity at Sigma. Yeah, and as he mentioned as well, like so we started or we started a while ago, maybe around 8 months or 10 months back, or maybe before that as well. So as just an initiative, and we could do some of the research. We could gather material across the internet and whatever is available, explored a lot of things, and collated our research into few of the documents and blogs. And as Mert mentioned, so one of the blogs which we have written, it is purely exploratory in nature, which caught their eye, and we are also very grateful to talk about our experience and how we implemented in this kind of a forum. Very excited about it. Yeah. So we'll go into the actual part of our experience and a few implementations which we did later. So I'll hand over it to Mert to ask everyone else to introduce themselves. Thank you.
Right. Thank you, Amit.
Amit, you're on mute.
Okay, sorry guys. Hello everyone. So myself Amit and I'm a data scientist at Sigmoid. So I'm working with Ashish and Bhaskar in many of the research projects and the business problems. So I got a chance to work on the quantum computing as Bhaskar and Ashish had already an experience in quantum computing. So it was a very fascinating field and we got some interest in it and we then explored the IBM Q and qiskit library. So we found some of the algorithms that were there already existing. We explored them, we went through some tutorials and all that, and then we tried to implement it by ourselves, and we were successful in that. We tried to compare our classical, we generally work on the classical computers and we generally run classical machine learning algorithms. So we wanted to explore quantum version of it and wanted to see how the runtime would change. So as a part of quantum research, we went through quantum support vector machine, and I had implemented by myself the following algorithm. And now I'm working in a big data architecture businesses problems and recommendation engine. So that's all from my side.
Thanks, Amit. Let's move on with the intros. I have a local participant with me who's my roommate.
Hey.
This
Hi,
is
everyone.
Santi. Can you say your affiliation and why you're interested in?
Yeah, for sure. So I graduated Stanford a while ago with a physics degree, and I'm working on a little startup here with Mert, having to do with quantum computing and finance.
Okay. Alexander Dakos. Alexander Dakos, would you like to introduce yourself? Hello. Okay. So we can come back to you. Anirudh Rawat. Sorry if I'm butchering names, by the way. English.
It's Anirudh,
Yeah,
but it's
and
okay.
is also part of the Sigmoid group, and he is going to be one of the presenters for one of the blogs that we've discussed. But Anirudh, please go ahead with your introductions.
Yep. So I'm Anirudh Rawat. I have done my bachelor's and master's from IIT-Kanpur, and there I had not a couple of more than that subjects related to or electives related to the machine learning applications. I have did a project there under one of our professors. So that particularly interested me. So just after graduation, I joined Sigmoid as a data scientist, and after that, I got this opportunity to work in this quantum computing research under the guidance of Ashish and Bhaskar. So that particularly interested me on the physics side also, and based on the application, it has numerous applications. So we have tried implementing a couple of them based on the resources that we gathered. So yep, I'll be showing one of our applications other than QSVM, but we are still working on it. We have done a version 1 kind of thing. So I'll be showing you that in the follow-up session. So yeah, that's it from my side. Thanks, Mert.
Yeah, thanks. Arizu Nayabi.
Hello everyone. I have an MSc in Embedded Systems Engineering from the UK, and as I gonna apply for PhD studies related to quantum technologies, I'm interested in to find out some research and some opportunity related to quantum technologies before studying PhD for that. That's it.
Thank you. Bharat Ram Ammu.
Yeah, hi everyone. I'm Bhaskar Ammu. I'm working as data scientist in a fintech startup in Belgium. To be honest, I'm here because I'm brother of Bhaskar, who's one of the speakers here. So apart from that, I did my master's as well in computational chemistry, in which I've gone through a course for quantum physics and quantum chemistry as well. I'm just going through, and of course I work on machine learning applications. So I'm just looking forward. I just googled it that it's connected to entanglement, and yeah, some of the concepts. I just want to link the interdisciplinary concepts between quantum physics and machine learning. I'm looking forward for that. Yeah. Thanks.
Amazing, thank you. Brian, hey, nice to see you again. Brian Liu.
Hi, Mer. Nice to see you again as well. Hi everyone as well. Nice to see you all. My name is Brian. I did my bachelor's in math and physics and graduated last June. What a legendary year. And then now doing my master's in computer science. I'm also really glad to hear that this talk will be about something we'll have a more applied perspective on quantum computing. So I'm very excited to listen to this hands-on talk and then gain some skills from that. And so nice to see you all.
Perfect, thanks. Gautam Chander. Gautam Chander. Okay. Jamie Gill, nice to see you again, Jamie.
Hey, Mert, good to see you. Just kind of like met Brian on like the last call like 2 minutes ago. We were just on the same Zoom call too. Good to see everybody. I am now at Stanford, at least for this quarter, doing a few courses to sharpen my skills up. So I keep learning quantum stuff. So thanks for Stanford to step up and Alexia to keep on doing this, because I've enjoyed all these quantum conversations over the last, I think we're on, what are we, 7, 8 or something like that right now. They've all been good. So looking forward to another nice day.
Very cool, very cool. Which course are you doing at Stanford?
I'm in CS 254, computational complexity. I'm also going through Amir's course in quantum hardware.
Is Avia teaching 254 complexity?
Li Yang is teaching it, and then he's teaching, I might stick with it. He's teaching 254B next semester, and he's also doing a research seminar. So I've definitely been enjoying it. It's definitely a good idea.
Amazing, amazing. Jayant is also from Sigmoid.
Yeah, hi, I already introduced myself.
Oh, you did, sorry. I'm so sorry. John Kostomsky.
Okay. Hi, John, you may be muted.
Zooming etiquette, I have some experience in modeling. I have a small company called Tandoor Data, and I'm really interested in quantum, where it's going to go, and the spin-offs that are going to come out of it, if not directly, but indirectly with all new technology. My degree is in business, but I got it because I was in IT for the longest time, in and out. Right now, I'm just upgrading a lot of AWS skills, because as I get back into going for more data science, I want to have the tools that I think are there, that just once you learn how to use the tools properly, then you can just think freely and just play with it, and if you're willing to pay for it. Now, IBM, I haven't played with that much, but in my experience with IBM up the street here in Dallas, essentially I attended a blockchain, and I was quite impressed on how much their system worked properly, because I'm the kind of guy who likes chaos theory, like what happens if I pull the plug in the middle of something and see what happens. And that's kind of like worked really well. The recording worked. And when you can trust systems that well in testing, because that's in my early days back in electronics, I was a test technician for like 5.5 years. So that gets ingrained, and when you start to experiment, what happens, and is the evidence that you're accumulating actually true? and then you have to go back and test and make sure. So you're constantly refining in the data that you've originally set out to follow your hypothesis.
Great, thank you. Katerina Pistunova.
Hi, everyone. I am a physics PhD here at Stanford. I've been working on nanomaterials and quantum materials for many years. First, electron transport and superconductivity, and right now I'm doing more optics. Yeah, and since I'm at Stanford, I've decided to take a couple of machine learning courses just to broaden my perspective. So yeah, just want to see what is out there.
Perfect. Karan Davuluri.
Hi, everyone. Am I audible?
Yes.
Okay. Hello, everyone. So I graduated in 2020, and I'm working as a project associate at IIT Chennai in the domains of deep learning and computer vision. And I came across quantum computing around 2 to 3 years back, and I started exploring about it, but got too closely related with it just 6 months or 1 year back, and have completed some courses, and I'm here actually really to learn something, and if possible, if I can get an opportunity to work in a research project based something of that sort. So I really look forward for the session. Yeah, thank you.
Thank you. Veso.
Hi, my name is Veselin, and I'll drop in the chat some information for people who may want to get in touch with me. I'm a mentor for the Open Quantum Software Foundation. We just finished one batch of mentees, and we are starting a new one. What we focus usually is working with students and computer scientists interested on specific project in quantum computing. So if any one of you have a specific project that want to work, I would suggest you can look up the program. And also I teach introductory class to quantum computing for some of the affiliations of my institute for advanced physical studies in Sofia. But I'm located here in California.
Thank you, Veso. Nathan Shore.
Hi, good to see you guys.
Good to see you.
So I'm a bit of an odd bird. I'm retired. Always had a fascination with math and science. I spent 5 decades in IT, sales, marketing, sales engineering, and the like. So I was really enjoying myself learning quantum math, and then COVID came along, and given my age and stupidity, unlike you guys who are smart, I've smoked all my life. So no one ever survived COVID with emphysema. So 9 months ago, I went into deep hibernation, and obviously it's still working. And the quantum is, I'm glad I did it because it saved my mind. I've had something to focus on during all these times. And I'm glad to report next week I get my second dose. So we're all getting there, by the way. And I think by the summertime, everyone will have it. And by the way, just to end, it's an endorsement to technology that they were able to pull off a vaccine in 1 year, and actually one that works. And for example, with AIDS, they've been trying for 10 years, billions of dollars, and there's no vaccine in sight. So at least it's some light at the end of the tunnel there, and good news for technology. Maybe with quantum around, it wouldn't have taken a year. It would have taken 2 weeks.
Yeah.
Or 2 minutes. All right. Good to be here.
Thanks, Nathan. Tianyi Hao.
Hi, everyone. I'm Tianyi. I'm a CS master student here at Stanford. I have some research interest in quantum simulation as well as quantum circuits, and I'm curious to learn quantum machine learning.
Right, thanks. Raghavendra Singh. Okay. And I saw Beatrice join in, but is she still here? She's also from Stanford Quantum. And then Yosh is gonna be back soon, so he can introduce himself when he's back. But I can do a quick intro for him. So Yosh is a sophomore at Stanford, and he started leading the partnerships at Stanford Quantum Computing Association after I graduated. All right, I think that's all. Did I miss anyone? This is harder than it seems because Zoom keeps moving around the list. So if I missed anyone, I'm sorry, you can just introduce yourself. Okay, so Ashish, do you wanna start with the talk? Thank you, everyone.
Sure. Great. Thank you everyone for joining in. This is great to see such a good group of people here. For our presentation, I would request Bhaskar to share screens. We
Yeah,
have been able
yeah.
to build a presentation. Do you have the presentation rights, Bhaskar?
Yes, yes. Just
Okay,
a minute.
great. We'll certainly try to keep this as much as conversational as possible, but there's too much to cover from our side. Four speakers, I would consider myself as half, but we will use this as a visual aid for explaining whatever we talk through. Most of the talk will be done by Bhaskar, Amit, and Anirudh. They have been the ones who had worked on researching and building the blogs that we wrote. I will quickly set the context for the conversation to follow. Uh, Bhaskar, moving forward. So from an agenda point of view, what we would cover in today's session is brief introduction to quantum computing, some idea on the total amount of research that we have been able to do on quantum computing from Sigmoid side so far. Then Bhaskar, Amit, and Anirudh will take us through what was their journey in terms of being able to explore tools, technologies available in the market, their journey in terms of trying to find out what hardware is available wherein we can work to build or test such algorithms. One of these stories which I would want to bring up is that we wanted to initially work on D-Wave as well, but somehow we realized that D-Wave doesn't provide machines to run in the Indian geography. So obviously our first choice was IBM Q, and we were able to run most of our algorithms there. Bhaskar will walk us through that journey as well. Amit would be speaking about the QSVM implementation, the blog which caught Alexei's eyes, and that's why we are coming in here. So that's going to be our core presentation. We will try to spend most amount of time on that aspect. And the last but not least, Anirudh will be talking about Q-Gan. Part one of that is something that we have already researched. We have built or written a blog on that as well. There is a follow-up blog which is coming up on this topic, but it is held up because obviously we got caught up in some other things. But that blog is coming up soon. We would probably have it by the next month end. Quickly moving forward, I would briefly talk about Sigmoid. Bhaskar, on the next slide. So what we have is a brief introduction to Sigmoid. We were founded in 2013. We're mostly a data engineering, data science, AI, ML, and a data solutions company. Overall strength that we currently have is around 220 plus people working in data and analytics. Our growth has been phenomenal. We have received a lot of awards as well, primarily on our work in the data science and data engineering domain. Sorry. We are backed and funded by Sequoia, and as uh, moving on to the next slide, Bhaskar. On next slide, what we have are the areas wherein we generally work in. So these are some of the areas wherein we have been able to provide our services to our client set. The client set, as was mentioned in the previous slide, is more than 25 plus clients in the Fortune 500 group. The business use cases that we have worked on include the standard, but what I want to focus specifically on the rightmost column, which is our R&D initiatives. So quantum computing is one of our R&D initiatives. We have another group dedicated to working on reinforcement learning and the application areas of the same. Our core focus generally is into marketing analytics, and on separate notes, we also work on GANs, CNNs, RNNs. And another area that we are deeply interested in is federated learning. We feel that given the privacy laws, which are picking up pace in most of the geographies, federated learning would become a core wherein we are trying to run models on individual devices without hampering or without infringing on privacy of users. So with mobile devices, this would become the way modeling or machine learning happens. Quickly on to the next slide, Bhaskar. And before I hand over to Bhaskar to take us through the journey on quantum computing so far, I want to talk about the quantum random walks as well. I think it is probably more than an hour long talk, but quickly about the glimpse of the work that I was able to do during my internship. So it was supposed to be twofold. We wanted to work on building a string search algorithm in a quantum space, and we also wanted to build a graph search algorithm which can work again in the quantum space. We were able to implement in a theoretical sense or prove the capability of a quantum random walk to be able to reduce the hitting time for a certain length of string in an infinite length of string. So the core problem was that let's say we had a string, we had named it as abracadabra, and we are trying to find that string in an infinite length of alphabets. So it's a search algorithm which works in classical sense. It would take a polynomial amount of time to converge. So the hitting time to find that string in an infinite length of alphabets would be polynomial in terms of the length of the string that we are trying to find. With the quantum random walk applications and MCMC kind of simulations, we were able to record it in logarithmic time as well. So that was theoretical. We are yet to implement it in real world, but overall, that is a research which was something that I wanted to do more of, but probably at that point of time I was more fascinated with France than quantum computing. But leaving that apart, I think if we get enough time, if we get enough preparation, we would love to present the quantum random walk in our paper at that point of time as well in a separate session. Our core focus is going to be the blogs that the team has written. We will probably land on the blogs part in 10 to 15 minutes from now. Please bear with us, and I would ask Bhaskar to briefly explain about our journey on quantum computing and the tools and technologies that we've been able to explore so far. I would pause for a minute for any questions.
So I have a quick question. So you said you implemented the random walk work on theoretical grounds. So what did you mean by that? And if you have a paper, I would love to see the paper. So can you share the link on the chat?
Yeah, certainly. It's not a published paper. If it was published, I would do that. But the draft version of it, I would be more than happy to share with this group after this call, if that's okay.
Perfect. Thanks.
Certainly, we'll do that. I don't see any questions, but So in that case, I'll hand over to Bhaskar.
Please feel free to like shout out questions if it's very pressing, but we also have a questions session in the end after everyone speaks.
All right, great.
Okay, thank you, Ashish. Okay, you guys can hear me, right? Yeah. Okay. So, starting from where Ashish left over. So basically, I would take the part of walking you guys with a summary or like a generic overview of what we could accomplish in our research, in our short tenure of our research. So the core idea where we started was we wanted to explore quantum computing, its applications, and our ultimate motive was always to look at the applications in the machine learning domain, because that is what we generally deal with. And quantum machine learning is something which is a very something which is highly looked forward to by a lot of experts in the field, in the domain as well. So we wanted to get into the applications of machine learning and also the practical implications, where how ready the current quantum world is. So that was also one of our important you can say points to look into. So that is how we started our research, wherein we started exploring the concepts of quantum computing. So as I think in previous quantum conversations over here, so I went through few of them as well. So I think there were a lot of talks wherein few of the concepts were touched upon, and there were also few of the talks wherein how should or how can someone learn quantum. I think one of the sessions was great actually. So maybe if we had something like that at our disposal, we could have done a lot better job in getting this knowledge at a much faster pace, and also getting it at a much deeper level as well. But we used the resources available across the internet for to understand the concepts of quantum computing, and also and during this time when we started our research, even in a where we were in a nascent stage of our research, there was a kind of a bombardment of this particular news, wherein Google came up with a quantum supremacy experiment. I think a lot of us remember about that. So that is something which triggered the entire internet in a way. It shook the internet, and there was a tug of war between the giants about how can someone reach quantum supremacy. And we were not sure of what quantum supremacy was, and we wanted to explore more about it. So that is where we actually went all into this, wherein we tried exploring multiple tools. We got to know that there were a lot of tools at our disposal, wherein we can actually run quantum algorithms on a quantum machine or a simulator, which is like a supercomputer, which is designed to work like a quantum computer. So that is something which when we heard about this, and then we also went into multiple research papers, wherein a lot of research has been done on this field. That is something which we came across, wherein we saw few papers on quantum machine learning, papers starting in 2010, 2014, wherein people started how can someone convert a regular machine learning algorithm into a quantum to its quantum self like that. So, and what can it be? Can its applications be? So all the things. So those are our initial research and documentation which we did. So then as soon as we went into that, so we wanted to get into the exploration part of the tools and libraries available. So I know in the previous quantum conversations as well, and currently there are n number of tools available. A lot of companies, a lot of organizations, and also one of our attendees also mentioned there is an open source quantum research as well. So a lot of tools available for people who are interested or enthusiastic about the quantum space to explore and delve into the space. But like we did some in-depth analysis into the available tools and libraries which we could like gather at that time. In a way. So, and we compared the pros and cons of each and every tool and a library based on the ease of usage, availability, and coverage of libraries and algorithms. So that was one of our important parameters we used actually. So as Ashish mentioned earlier, so the first thing which we or the first company or like organization which we reached out to was D-Wave, because that was kind of like they were trying to build quantum machines, and they were ready to offer it to like anyone for free. So we reached out to them, but unfortunately we were not given access in the Asia Pacific region. So basically then our alternatives were IBM Q and Google Search and like Amazon's like one of the you can say a tool, something which we could not explore in depth. But these were the two alternatives which we had in front of us, and then we explored them, and that is how we chose IBM Q, which we'll get into some time later. Then we also went into the applications of QML algorithms. So QML is like a quantum machine learning algorithm. So we wanted to see like in the libraries of a few of these libraries, there were pre-coded, you can say, libraries which had a quantum machine algorithm coded. So like a QSPM or a Q-Gan or a variational quantum like classifier or something like that, wherein we generally work on classification and clustering problems like for clients, for business, to solve business problems. So we were intrigued about how can these algorithms work in the quantum space. And we also wanted to select specific problem statements like a classification problem. We also explored the breast cancer classification problem, or like because there was a data set available in the qiskit library actually, and the quantum SVM algorithm, which works as both classifier as well as a regression technique. So that was also available. So it was and it was related to breast cancer, which is much closer to my experience in my previous company, wherein I was working for a healthcare AI firm, where we used to predict patients you can say probability of getting like diagnosed for a disease, something like that. So we used to do all sorts of or solve all sorts of problems like this. So this kind of intrigued us. So like that is where we started using or you can say exploring these tools as well as the algorithms inside these tools and libraries. So once we went into these, we then explored different functions, syntaxes, variables, and the libraries were very fascinating in a way. So they have multiple branches and multiple you can say divisions for each and every specific application. Like example, machine learning was one of the subsections of this particular qiskit library which we went into. There were many other applications which we were not aware of in the first place actually. So it was very fascinating to see there were so many applications where quantum computing can be used. That was one of the fascinating parts. But like we try to focus on the machine learning part actually, like because that is what we were interested in. So like we tried taking some existing code and implementing it on top of a data set and running it on an actual machine, actual quantum machine, as well as a simulator. So this was our our work actually in a way, and we tested the codes as well. There were a few syntactical changes from a lot of resources we collected. So we actually tested that, edited it, and we also tried submitting few pull requests in terms of the syntaxes to the branches actually. But anyway, like now, if you see, like as a interesting thing is that the entire IBM Q and the qiskit library has gone into a complete overhaul that we ourselves cannot identify where is the thing which we actually worked on. So it's like, and they are doing a great, I mean, I can say like it's an amazing work actually. Their vision is great. and the way they have changed it, it is much more easier now. So for anyone who wants to start using or like implementing any quantum related algorithms, or like wants to learn quantum, we would suggest like that is a very good platform, IBM Q as well as Qiskit. So that's what, like we'll come to those like smaller details about those very soon. And the last part of our research here was like publicizing our blogs. So, like whatever we worked on, so we just wanted to put them in blogs so that at least like the common folks and our friends as well like could go through them, because this is something which is everyone's like interest, always at the back of their minds. They might not know like they're interested in it, but as soon as they see some content like this, they'll be very much interested. So that's what we wanted to trigger actually. So we wanted to put everything what we did in a blog. So though the blogs are not very much in detail, but like we try to maintain some amount of depth in it. So which we will get into later part of our presentation. So we'll see. So that is what is a summary about quantum computing. So now, like just quickly touching about the landscape which we landscape of the quantum computing research. So this is not the landscape across the world or like in the entire space. This is the landscape which we could see or the horizon we could look at. So we just split it into three things again: research topics, the tools explored, and the algorithms implemented. The research topics were mostly about the quantum supremacy experiment, getting to know what actually Google did and what maybe like IBM was accusing that like this is not true. And again, there were a lot of case like it was a tug of war actually. It was interesting at the same time. So basically, we wanted to get into the details about what actually quantum supremacy experiment was. We also published the basic understanding of our of us in a blog as well. Then we went into coding on quantum computers, understanding the circuits and gates, and basic principles of quantum computing like superposition, entanglement, and everything. And we also went into some research or like basic tutorials about standard algorithms like the Shor's algorithm or the Bernstein-Vazirani algorithm. So which was which were readily available in the Qiskit tutorial YouTube series actually. So it was pretty intuitive. And then we also wanted to implement a few of the kernel-based algorithms because of its ease of implementation in a way. Like that is what we thought. So SVM, which is support vector machine, which we will get into later, and KNN, K means PCA. So all these are basically kernel-based algorithms which have higher practical implication of a quantum side of it in a way. If so, and also quantum neural networks and recommendations are our ultimate goal. So that is our little far-fetched goal is to publish a paper about quantum recommendation engines. That is one of our far-fetched goal in a way, which we will hopefully achieve soon. So that is more about the research topics we covered, and the tools which we explored were these: the IBM Q and Qiskit library together. And we also went into D-Wave. We explored it, but ultimately we faced some challenges with it. So Google Circ and TensorFlow Quantum was also something which we explored, but like they were not as user ready then when we were exploring. Like we found IBM Q and Qiskit to be very much user friendly at that time, and right now as well. But like the other platforms also have amped up their game. Like every platform right now is very much friendly. So I think it's every platform is a go-to platform right now. But back then when we started, we felt IBM Q and Qiskit to be the most user friendly, and also having the algorithms which we implemented, like on the right side, like which you see, the quantum SVM for classification, the quantum GAN. So both of these algorithms were readily available. So we thought we will try just like a scikit-learn library. They have these algorithms mentioned in their or like written in their library, and which we can call upon and implement it on any of the cases. So like how to use and how to implement it is something which we had to learn. but at least like qiskit did the part of coding it out for us right from scratch. So that is something which is great. And there are also in our to-do list we also have quantum pca, quantum k-means, quantum regression as well, in a way wherein these are not actually currently available in this library. So this is something which we wanted to do or which we wanted to implement from scratch, wherein we want to come up with a circuit and to like calculate a quantum pca and quantum k-means clustering and implement it on an actual data and see how it works. So that is something which we are planning to do. So that's our landscape. Yeah. And again, so this is basically, I'm not kind of watching for a specific group here, like or IBM. As Alexi mentioned, he is like he's part of IBM, but like we are nowhere related to IBM or qiskit. But we found this so user friendly that like we wanted to watch for it, like at least in this presentation. So just a brief introduction about IBM Q and qiskit. So IBM Q like is a IBM Quantum. That's what it stands for, IBM Quantum Experience. So for someone, anyone like to just delve into the world of quantum. So this is one of the best starting points, you can say. So they have the only thing you need is a IBM Q account. You can create it through your Google account itself. So the best part about this is that you get to work on actual quantum systems. So there are 9 quantum systems available for anyone for free actually, and there are 11 more which are paid, I guess. And earlier there were very smaller machines. Now they have 2 qubit, 3 qubit, 5 qubit, and 16 qubit machines as well, which are placed across the world. And each system differ in qubit topology, a quantum volume, or a number of qubits actually. So basically, you can see which gates are specifically configured in a particular machine, and you can choose that machine for any specific algorithm which you want to run. So that at that level, like the you can say the details have been mentioned there. And like coming back to qiskit, it's an open source framework. It's similar to any algorithm, or you can say any algorithm consisting library. So qiskit is all about like circuits, the quantum algorithms, like how do you access the hardware, how do you trigger a simulator, how do you trigger a quantum machine, how all those, and like how do you like get into a result, or you can say measure something. So all possible like quantum applications are coded in qiskit. So this is the most important, or like the you can say heart of this entire thing. Also, like our main reasons for choosing this is that like we can readily have this QSVM and Q-Gan like algorithms here, which we the classical part of which we are kind of aware of. So we wanted, like, why not try this? That was our main motto. That is how it is. Okay. So yeah. Then coming back to like, so this particular slide is just a preparatory slide for the slides coming ahead actually. So I just like put across like few pointers about the quantum gates and quantum circuits. So just before that, just wanted to touch base on like very briefly on the quantum properties actually. So this is where we started off with. We understood what superposition was. So wherein like it was kind of difficult for us to understand what superposition was, because like it is very difficult to visualize something in the quantum realm. So as we see like something everyone's pretty like no, or everyone must have watched the Ant-Man movies, wherein the entire movie, like the only word I could listen to was quantum. So I was kind of fascinated right then, but like we could not understand like what exactly it related to. So then like understanding these properties and going into depth of it, like the superposition wherein a qubit or an electron, you can say, can be in the states of, or can have an upper spin or a upward spin or a downward spin, you can say. So this understanding this concept was difficult for us initially, but like later on, this is something which we could like understand in terms of the practical machines which were being created. Like few machines are based on electron based machines. Few are you can say the charge is something like maybe superconducted materials would be used. So basically the charge is a positive or negative. So so that's what we understood, like how something a qubit can be in superposition. And we also like understood like what entanglement was, like wherein when you have one qubit, so basically qubit is again like a building block of quantum realm, you can say. So if there are two qubits, so two qubits can be connected to each other, and both the qubits like, can be only be measured without one another. So that's like pretty much in a single sentence if I have to summarize entanglement. And this was also very like important, wherein like this can be or quantum qubits can be put into entanglement using few quantum gates. So that was one more information which we could get. So that is again a basic thing which someone would go through while going through quantum computing. So quantum gates and quantum circuits, these are the basic building blocks of anything, like any algorithm which we have to build, be it a quantum machine learning algorithm, be it a optimization algorithm, be it like you can say anything, any kind of an algorithm, or a mathematical solver or something. These are the ones which someone has to focus on. So there are like one qubit gates, multiple qubit gates. So a gate is as simple as a classical gate. So wherein it's an AND gate or NOR gate, that is a classical gate. When it comes to a quantum gate, there are multiple gates which you can which there exist. You can also create your custom gates in a way using IBM. There is something called as quantum circuit builder in IBM Q, wherein you can position your gates on it and like see how would a qubit change its state, because a qubit can be as we talked about in a superposition, so it can have a probability of both 0 and 1, so it can be in both the states. So you can change the state using these gates. So all the quantum gates are reversible, and they are usually represented by unitary matrices. So for someone who is interested in understanding the calculation behind it, so matrix representation is very easy for someone to understand it. So these gates can be represented in unitary matrices, and multiple qubit gates exist as well, like the swap gate or the C0 gate or the CZ gate, um, wherein you would like work on like at least two qubits to get your output. So basically, if you are in any kind of a gate, there are like two if there are two qubits, and the output also would be two qubits. So the number of input qubits would be the same as the output qubits of any gate. And you can say like the quantum circuit is again like is the main thing, like wherein which would transform or manipulate the qubits. So just like a sequence of ones and zeros is manipulated by a classical computer using gates, the quantum circuit manipulates the qubits. This is what would change the quantum state from an initial state to a desired probabilistic state. And also this is what is required to change or like convert a classical data into a quantum data as well. So that is like pretty much about the quantum gates and circuits. And like yeah, one of the last things just to touch upon this, I know this slide has a lot, but like effectively it is mostly related to the later part of the presentation. So quantum machine learning, this is just a very easy way of putting it forth. This is something which will be gathered from a lot of research papers actually. So what we see is like a quantum machine learning algorithm is a quantum algorithm which is as simple as like which can solve the typical machine learning problem, but can also use the efficiency of a quantum computing, you can say quantum computing in a way. What do you mean by that? Is example, if someone wants to like work on a support vector machine. So the quantum approach would help us calculate the distances basically, because all these like k-nearest neighbors support vector machines and k-means clustering have some other way like an integral part of it would be calculating distances between points in any n-dimensional space. So this calculation is something which can be like sped up like by some to power something n-fold through this quantum approach. So that is why this quantum machine learning is kind of is one of the things for the future. So similarly for neural networks and decision trees, we see the first explorations of quantum models, like wherein that is what we have mentioned here, like a quantum approach, but like a lot of like you can say like leap in this particular area. Like, and onto the right, this is one image which we are very fond of in a way. So this was something which we found on one of the like GitHub repositories of some person. Like this was across the internet as well. So this particular image gives us or like beautifully explains us like the correlation between, or like the intersection between the machine learning realm and the quantum information processing realm, or the quantum computing realm. So the circle or the, you can say, vowel inside it is the quantum machine learning, wherein quantum annealing, quantum topological algorithms, all the algorithms which I just mentioned, the quantum PCA, SVMs and everything, and control methodology, metrology related algorithms. So all of these would be an intersection between the machine learning side as well as the quantum information processing side. So this is pretty much the like the quantum machine learning related like you can say theory, you can say. So now what we could do was we picked up one particular algorithm. Like it could have been anything, but we picked up SVM because that was readily available in the library. And then we went into implementing it and looking at the practical side of it, though we could not get an actual, obviously we are still at the like noise, we are far away from the fault tolerant quantum machines kind of a stage. So, but still, like we wanted to understand the practical implications of any quantum version of a machine learning algorithm. So that is where we picked up a QSVM and a Q-Gan. So I think like I will like Amit to take or like take you guys through the actual implementation we did on the quantum SVM and quantum Q-Gan actually. And like yeah, Anirudh will be taking you through the quantum Q-Gan implementation. So quickly over to you, Amit. And before this, like if you have any questions, we can take it now, or we can take it at the end of the session as well.
Good.
I have a question. Can you hear me?
Yeah.
Please go ahead.
Oh, sorry to interrupt. Hey, Bhaskar, hi, it's Kevin Roney.
Yeah.
There's just so much interesting stuff happening here. So many great, interesting frontiers, and the engineering cutting edge on these quantum systems. It's evolving rapidly. It's unclear to people who are not full-on practitioners which specific algorithm, especially within the machine learning domain, will make a supremacy style a breakthrough with broad commercial applications, because there's many different options here. It's unclear who is in the lead to do really the big commercial breakout. What do you think?
Well, that is the big question, right? I don't want to interrupt, but yeah, I would love to hear about this as well.
Yeah, that's the big question.
Yeah, so again, like this is something like who is in the lead in terms of algorithm? That is what you want to understand, or in terms of
not in terms of a company name, but no, rather in terms of the specific domain of application down to a specific algorithm. I mean, it could be SVM, it could be PCA. I don't know, but it's hard to see the landscape with clarity now.
Yeah, okay. So just as hard it is for us to understand, it's as hard it is to explain in a way. I would say if Ashish can help me answer this, but I would say that all of these, like you can say, all of the algorithms currently are not practically usable in a way as of now, as per my knowledge. So we could only just see or implement a couple of them. There are a lot more. So SVM is one of them in a way, like that is one of the classification algorithms. You know, it can also be used for regression actually. But the thing is, practically, if someone has to use it to achieve supremacy or like or a time advantage, can say, over a classical machine, it highly depends on the hardware rather than on the software. So hardware is not that ready according to me, but someone can correct me if I'm wrong. That like there is so much to do about the measurement part of it, the fault tolerance part of a quantum machine, and also if you see, we currently are dealing with a very small sized qubit machine, like maybe 10, 15, 16, or Google's quantum supremacy was achieved on a 76 or maybe 72 qubits of a machine. But the thing is, for something to be implemented for a business application in a way, or an algorithm to be implemented, we need much more qubits than that, because the amount of data we have is also huge. So like the Google's quantum supremacy was just to generate a random sequence and replicate the sequence. That is not an actual practical implication, because a quantum SVM can solve like a patient's prediction of maybe cancer or something on a classical machine, and that too on a huge data set. But that is not that easy on the quantum side. So basically, none of the like algorithms are in lead, you can say, in according to me. But like if there is something else, if Ashish wants to add or someone else wants to add, they can.
Yeah, sure. I think yeah, Kevin, I think that's a great question. I think everybody's trying to find a solution to that or an answer to that. What's going to prove that quantum computing is worth it? From our experiments as well, what we wanted to test was that does quantum computing based analysis brings in real speed improvements, efficiency improvements. We were not able to observe it so far. Amit and Anuruddh would cover that in our blog analysis as well. Primarily because the major part of the competition went into converting the classical data into quantum data as well. But and being able to run quantum algorithms on top of that, there was something which was a challenge. Now, addressing your question, I think the first thing that I see, the area which would be impacted the most, I think is going to be the encryption, decryption, and the password and policy protection, privacy protection. That's the area which is going to be impacted fastest or earliest because of quantum computing. And again, it's a bad way to put it, but I think it will start because hacking would become very easy when quantum algorithms start functioning at their potential. And then obviously the other part of it, which is being able to make more secure passwords, make more secure apps, that area would pick up very fast. I don't know, can't say certainly, but from my point of view, I think neural networks are the areas which are going to expand. So the complexity that we see currently in neural networks, which makes it unobservable or unidentifiable so far, would expand further, and that is where the quantum computing algorithms and calculations, the complexity, the computational ease would help best. That's our hunch. We don't know. We are also looking forward to exploring that area.
I wish you luck. A fascinating question. Thank you.
Yeah, let's please come back to this though. This is a great discussion question, and it would be great to hear everyone's thoughts on this. Thanks, Kevin.
Yeah, I'll continue on the quantum SVM implementation. Thanks, Bhaskar, for
Sure.
giving the overview landscape on quantum computing basics and quantum machine learning. And thanks everyone for joining and giving us a chance to speak on the experiments that we did. So Bhaskar had already discussed
Amit.
about the quantum machine learning landscape, right? So one of its application is quantum support vector machine.
Amit, I'm so sorry to interrupt, but quickly checking with the group as well. Are we going slow? Are we going fast? Are we covering too much basic stuff? Please let us know. We will ramp up on that. We're doing good.
I think it's fine. It's good if we start the discussion around 5, maybe 5:10, but if that's fine.
How many minutes do we have to cover our presentation?
So maybe 20 minutes to half an hour. Is that enough?
Okay, I'll then quickly walk you through our presentation and let Anirudh give his order. So what quantum support vector machine is, it is a quantum enhanced version of the support vector machine. And what is support vector machine? Is it a supervised learning algorithm that we generally use to classify the data, and sometimes we solve the regression problem with it also, right? But mainly we'll keep our talk around the classification part only. So let me brief you about how the support vector machine works. And there is no much difference between the working principles of the support vector machine and quantum support vector machine. The only difference that we face is the calculation part and the computational expense that we are reducing using the quantum phenomena. So support vector machine works on the principle that it classifies the data in the, suppose the data is in the 2 dimensions. So it tries to find a line that will separate the data, and there can be multiple tons of lines that will separate the data. So how do we choose between these lines is the question. So what the model learns, and tries to learn is, it creates 2 lines. We can in layman terms call it as a tunnel. On the either side of the tunnel, the data point will reside, and then no data in between the tunnel. So the model tries to maximize this margin, and as the model iterates through the data points, the parameters of the hyperplanes are determined. So after getting the two hyperplanes, or say in 2-dimensional line, we get an average line between these two, which would certainly be the best line that would classify our data point into 2 classes. So when we speak it in 2 dimension, it looks so simple, right? But what if we took if we see a real world problem where the data set is too much complex that it is hard to separate it using a single line? So in that case, we can't use a linear SVM, of course. So we go with the kernel SVM and use that kernel tricks that is readily available for the kernel algorithms. As Bhaskar has already mentioned, that we use kernel algorithms wherein we only want to calculate the distances between the data points, right? So in case of SVM also, the objective function that we are going to see here is calculating the inner product between the data points in the hyperplane, different data points, and learning to try to minimize this objective function so as to get the parameters of the hyperplane. So what if we the data is not linearly separable in the given dimensional space? So what we need to do is map it to the higher dimensional space and then do the inner product in that space, right? So it can be so much computationally expensive if the dimension of the transform space is too high. So as we can see that phi is a function. Let us suppose that phi is a function to map the data point from the input space 2 dimension to say 3 dimension. Then the cost will be not that much, but if we say about the dimension would be 10-fold or 50-fold, then the computational cost will be so much, just because first we need to calculate the data points that are in the original space and map it to the higher dimensional space, and then calculate the inner product in that space. So to reduce this computational expense of the algorithm, what we introduce is a kernel trick, kernel algorithms. What kernel does is it calculates the inner product explicitly without visiting that space, and result the same scalar value as the inner product would have we would have get in the higher dimensional space. So this is a kernel trick that that is there, which will reduce our tension, or which will reduce our task computational expense so much. So this is the basic of support vector machine. Now we will come to the quantum version of it. So coming to the quantum version of it, there are 3 basic steps that is in a quantum application or any quantum algorithm that is processed. So first we need for performing any quantum say quantum operations, we need the data in the quantum format. Either we generate it from the quantum machine, or we can get it from the classical data and we can transform it by applying some circuit and transform it to quantum data. Then we do some processing, and the processing part can involve doing some PCA, doing some operation, logic gates operations, so as to do the task of the algorithm that we want to run. So, right, in case of the support vector machine, we want to classify the data. So that processing part will be the step 2 of our high level overview. And then we take the measurement in the higher dimensional space so as to get the classical output. So quantum support vector machine does 3 tasks. First, it converts the classical data into quantum data, do its some processing part, and then we measure the output so that we can classify the new data which is unlabeled. So coming to the practical implementation. So what do we need? How do we proceed with the implementing our algorithm, or how do we write code in library? So the basic implementation involves creating an IBM Q account. What we did, created an IBM Q account, used qiskit library, used its inbuilt functions and feature map. That is, feature map was used just to convert the classical data to the quantum data. Then we used the breast cancer dataset, which was around 569 records and having 32 parameters. So we can't run all the 32 features on the quantum machines because in order to run that, we need to have 32 qubits, and that is hard to get at this point of time. So what we did was we did some PCA, reduced the 32 features to two features. Then we selected 2 qubit machines. Then we defined feature map with second order expansion, as we had only 2 qubits. We made the entanglement. Then we created a quantum instance, or we created we called a quantum estimator, which will be training. Then in order to train the quantum instance, we need some backend execution settings that is there in the IBM qiskit library. So we selected backends as a IBM Q simulator, and also at the same time we ran our algorithm on the IBM Q machine. So in order to run the algorithm, we have created an estimator. We have bring out a quantum instance. Using these two, we can easily input a train and test data set into the estimator, and we can run an algorithm. So algorithm will learn to classify the data by learning the weights of the data points, and at the same time it will give the importance to the sum of the data points that would clearly affect the equation of the hyperplane. After that, once the data set training has been done, we can easily make the prediction using the quantum instance and qsvm.predict function that is there in the qiskit library on the selected test data set and the quantum instance. Now, quickly moving on to the next slide. This is the high level architecture what I have just explained. We did loaded the breast cancer data set, then did some PCA, imported IBM Q library, loaded IBM Q account, and bring out some feature map, quantum instance, execution settings that we wanted. Combining all this, we have created an instance of quantum support vector machine with the test dataset, train dataset, and the predefined feature map. And then after training the model, we got the classification result. We did some analysis on the classification result, and we come out with some metrics that I'll discuss in the later part of the presentation. So moving on to the next slide. This is overall view of how feature map actually works. So feature map is a general work of the feature map is just to transform the classical data to the quantum data, right? So the algorithm works in the same way as the classical one. The only idea behind the quantum kernel is that it tries to calculate the inner product, but on the quantum data, not on the classical data. So in order to define a feature map, there must be some entanglement, as Bhaskar has already applied mentioned that entanglement is done between the qubits so as to measure the output of the one qubit. The other qubit is also being kept in interaction, so that we can build a circuit that would perform some operation and get the desired output. So there is a different types of entanglement that qiskit provide. It is one of it is linear, one of it is full. So linear entanglement is something which is one qubit is interconnected to the next qubit, and the next is connected to its next one. And then in case of full entanglement, all the qubits are interconnected. But as we are running our algorithm with two qubits only, so either we take it as a linear entanglement or a full entanglement. Nothing matters, because the two qubits are only there. So the interconnection between those two will be a simple connection, which we here can see by the CNOT gate that we have used in the first image. We can, if we are using the multiple qubit machines, or if you are using going for the higher dimension, this is for the purpose that if you want to go for the higher dimension, we can explicitly mention an entangler map. It can be entangler map is nothing but a dictionary which defines the interconnectivity of a source qubit to the target qubit. We can explicitly mention it in the feature map that we are using. The feature map can be second order expansion, Pauli's expansion that are there in the qiskit library already. So how this feature map actually works, the math behind all this can be seen in these equations. So what it does is, first, in order to classify, transform the data, we need a unitary operator, which is nothing but a breakup of three phase shift gate and two control node gate, which is just to control node gate are just to create an entanglement, and unitary gates are just to rotate the qubit into different phases, convert it to from classical data to quantum data. So the unitary gates that we are using is U1 gate, that the metric of which is shown here, which is the diagonal matrix of 1 and e to the power I lambda. So here phi is a function that we are using, set of functions that we are using to transform a data set from a lower dimensional space to higher dimensional space. We are using this also to calculate the kernel matrices that we are going to get, or we are going to need in our determining our hyperplane. So talking about the unitary matrix, that is the second equation. This is the general equation which is working behind all the circuit, right? And we can explicitly define our circuit, or the qiskit library is already developed so much that it is already providing the second order expansion as a function, which inherently creates this circuit for us without delving into the equations and creating it manually. So after creating the circuit, like in the third figure, or in the second figure, we can see that there are blue and red lines, which means that we are using only two qubit machines, two qubits, so that only two lines will be active and the rest are not needed for us to perform our calculations. So this is overall how feature map actually works, how it transforms the data set, how the kernel is calculated. We'll see in the next slide. So this is the general maths behind how the kernel is calculated. So we can see these are the system of equations that is being solved to get the parameters of the hyperplane. K is a kernel matrix that we already have seen that it is used in place of the inner product if the data set is transformed to a higher dimensional space. So K is a kernel matrix which we need to determine, and the only need of a quantum computer, or only the quantum part that is being processed here in the QSVM part, is the estimation of the kernel matrix only. Rest all the things can be done classically also. So the kernel estimation, which is a time taking process, is done in the quantum way, and the rest all the processes is done in the classical way. So K is the kernel matrix that is determined, or the which is kernel function already that we have created a circuit. We have built-in feature map, which is second order expansion. They do a task for us, get the inner product of the data, and y here represents the level of the classes. It is predicted. If it is a positive, it is +1. It is negative, it is -1. So only thing we need to determine is the hyperplane parameter, that is b in alpha. So in the image, you can see the simple linear equation, which is wx plus b equal to 1, 0, and -1. So w is similar here to alpha, which is a hyperplane parameter, or we can call it as a slope. So once our kernel matrix is calculated in the quantum fashion, we can use it. We can use it to now calculate the hyperplane parameters. Hyperplane parameters are the only unknowns in the above equation. And then once the hyperplane parameters are with us, we can classify the new set of datums easily by inputting our suppose x0 is a data point which we need to classify. So we can easily put it in the equation, and we can apply the sigmoid function. So it will return a output as a +1 and -1. So in order to calculate the class for the new set of datum, again we need to calculate the distances of the new set of datum to each and every point in the feature space. So again, the quantum part is involved here, which is the calculation of the kernel matrix for the new set of data. So we have seen that quantum phenomena is called twice in this protocol. First, the kernel matrix is calculated for the set of datum that is already labeled, and secondly, the kernel matrix is calculated in the quantum fashion for the new set of datums. And these two are the time-taking process. If we do it classically, which should ideally be not taking time in the quantum version by making it parallelly, or making it kernel, making use of the kernel in inner products in the feature space. Now, using this equation, we can easily classify the data in the positive class or the negative class. So this is a high level overview of what the maths is going behind and what is the quantum part that is involved. Now coming to the implementation part, we have simulated our 4 experiments, which was on the breast cancer data set. One was on the entire data set with all the features. That is not relevant in this case, because we can compare the result of the algorithms that are similar in nature, right? So what we did was we were using the quantum support vector machine with only 2 features. So we also performed the support vector machine classification problem with 2 principal components, and then we analyzed the confusion matrix. Confusion matrix is essentially distribution of the data points as a true positive, true negative, false positive, and false negative. So we generated a confusion matrix. Then we went to calculate the recall value for the SVM with the classical data set with 2 principal components, and performed QSVM with 2 principal components on the simulator. That is, I think, quantum 16 Melbourne simulator, and then which was a quantum IBM Q real-time machine, wherein we performed, and we got a recall value of this to be 0.931 and 0.8. So quickly explaining, recall value is nothing but of predict of how many actual cancer patients, if we say how many were predicted that they had cancer. So in these type of problems, that recall value is much more important than the precision or accuracy, just because if we are not able to classify the cancer patient as a cancer, then it would be a life taking for that person, right? He will not go for the diagnosis, or he will not go for the treatment. So we mainly focused our experiments and tried to calculate the recall value. Although at this point of time, quantum machines are not quantum machines, and we can also say quantum simulators are not that accurate that it could classify all the data points correctly. Classifying it classically gives more accuracy. The only advantage that we get here in the quantum, or what I actually observed, is we could get a runtime, like we can reduce the runtime of the learning algorithm. But the question that Ashish has already answered, right, that we did not see any runtime reduction while using the quantum support vector machine at the I have applied it few months back, right? It took around 20 to 30 minutes for calculating or estimating the kernel and giving the predictions. For the 20 set of data points only. And we can run classical SVM of hundreds of data points or say thousands of data points within a fraction of a second. So I didn't see any advantage in terms of the time reduction, and we can't at this point of time expect the accuracy part just because it is in the development stage. And I think by the time we have applied the QSVM algorithm, and by the time by today when we see, there must have been some certain improvement in the classification accuracy and the recall value, just because I have visited the qiskit library and I have seen that there is a lot more advancement in the feature map that they are providing. And the feature map is the basic circuit, basic way to create a circuit, and the operation that we provide in that circuit ultimately decides that what will be the recall value and accuracy. So this is all from my side. If any questions.
Do you mind if I chime in again? I'm wondering, I'm not sure if I saw all the details on your kernel approach, but in the classical algorithms, you usually have to pick a class of kernels for the feature map. In this particular implementation, are you claiming there's a level of generality with respect to the kernel where you don't have to tell it what type of kernel to use?
Nice question, but the answer to this is that the second order expansion that we are using here and the QSVM estimator that we are using here, qiskit has already inbuilt what say kernel function that they already defined in the estimator itself. It is RBF kernel at that point of time when we are using the second order expansion. Depending on the feature map, that was that I was talking about, that feature map decides that what type of accuracy we will get. And accuracy can be related in terms of the kernel function that you are talking about.
Yeah.
So kernel function depends, or I would say that qiskit is already like introducing the kernel function itself in their code library. So we need not to explicitly define it.
Thank you so much.
Yeah.
Anirudh, you can start with your part.
Sure. I'll go ahead with the Q-Gan.
Sure. Last leg of our talk. I think it will take another 10 to 15 minutes. Then we'll hand it over to you, Matt.
Okay, great. Thanks.
Cool then. So before going into the Q-Gan, I'll first brief you all about what GANs are. So GANs were found in, like, they were generated by Ian Fellow in 2014. So it's basically a great advance in machine learning. So they have numerous applications, and one of the fanciest that I feel is a face generation. So basically there is this page called that this person does not exist.com, which shows you a face every time, and it seems real but it's not. So yes, it's one of the great applications of GANs. So basically GANs is like a generative modeling approach using the deep learning methods. So it basically has uh, it's a game where there are two players, both of them are neural networks. One is generator, one is discriminator, and the goal is to generate data that almost resembles the data that we are providing as a training set. So the generator keeps generating the fake examples, and both the real examples and the fake examples go into discriminator, and discriminator tries to detect which one is real or which one is fake. So there are these two neural networks, one is generator and one is just discriminator. And based on the loss functions that we calculate, these are like the weights of both of these neural networks gets updated, and eventually it like the process would stop when the generator is generating almost as real image as it is, or as real example as it is in the real data. So as shown in this architecture as well, like the generator generates a sample, there are samples from the real world examples, images, and goes into discriminator and finally detects and calculates the loss function and then eventually improves the model. So this was the overview of GAN. Now let's look into a bit of mathematics involved in GAN, like the loss functions. So Bhaskar, can we move on to the next slide? Yes, so basically X is the real world examples, the sample from a distribution, let's call it PR or P real. The G is the generator, D is the discriminator, of which the output, that is 0 or 1, but it's a probability on which we say it's 1 for real or 0 for fake. So generator loss function, it gets calculated using the output which discriminator gives, that is d of g of z. So we calculate it using negative of the log for each sample, and then we like basically average it out. And for the discriminator loss function, it gets divided into two parts. It like the discriminator has to tell if the image or data from real distribution is real and the fake is fake. So it has two components, one for real and one for fake, and similar calculation gets done. So basically the training gets over when these both gets into a Nash equilibrium. Since it's a game, we can see it from the game theory perspective. So basically the generator is trying to fool the discriminator, but the discriminator tries to, like, it tends to see if that generator, it classified it as fake. So yes, so let's move into the Q-Gan part. So the Q-Gan, so basically there are three main components. One is the real training data that we are providing, one is discriminator, and one is generator. So based on that, we can see different scenarios for implementing Q-Gan. So the first one, which is stated here, it's like it says data quantum, discriminator quantum, generator quantum. So it's basically the best scenario for quantum, where we can like actually perform with greater efficiency. But since the systems are not that fault tolerant, so we are not able to implement that now. So for now, what we have implemented, we have taken the classical data set, the third one that I'm talking about. The discriminator is classical and the generator, that is generating in quantum. So we have implemented this one since it was the most practical application that we could think of at that point of time when we were applying. So Bhaskar, can we move on to the next one? Yes, so basically this slide tells about the Q-Gan generator circuit. So Q-Gan is basically a parameterized quantum channel where we have like n qubit input state and n qubit output state. So the expression tells about the input state uh, of this, where p j theta is the like resulting occurrences of each of the states. So the quantum gate, that the quantum generator is implemented by variational quantum circuit. So there are like this alternate layers of gates where each qubit that we have, we apply the poly y gate, which basically changes the y component by pi radians. And between two of these units, there is one like this control z gate, which is like entangles two qubits. So there's this truth table for this particular, that when like there is one what do I say, control bit and one is target bit. So when one is 0 and other one is 0, it gives the same output. It won't change the target bit. It will only change when both of them are 1. It will change the target bit with, like, it will flip it, the it will flip the z component of it. So yep, so when we like uh, when we start like with the initial state, so that will like it, that will mostly tell how much time it is going to take in application, since it's a process, and after as many iterations, if we start good, we finish early. So that is the scene. And so how we did the optimization, so basically the classical discriminator, it's a standard neural network with the sigmoid activation function. So we have m samples from the real world data, the actual data, and we generate m samples from the generator. So based on these, both of these, we train the discriminator and we calculate the generator loss and discriminator loss. And since if one gets minimized, the other one gets maximized. So it's basically a min-max problem. So we try and find Nash equilibrium, or both of, or a point where both of these converge, or like basically these are optimized based on the two parameters, the phi and the theta, for generator and discriminator respectively. So yep, so this is the architecture that we followed. Like from the quantum backend, we pull qiskit library, and like for this particular experiment, we generated, for the real data, we generated some 1,000 points from a log normal distribution, and we put that into a quantum circuit so as to change, since the generator is like, and outputs the data in quantum format. So for changing the format, we push the real data into the quantum circuit, which finally goes into a discriminator, and from generator it goes to discriminator and the output, and then we evaluate the metric, the loss function, and eventually it trains the model again based on the number of epochs and number of iterations that we provide as input. So for generating this output, these like some of the graphs, so we use some of the parameters, like we defined number of qubits, we defined the mu and sigma for this log normal distribution, we define number of epochs we want, we define the batch size for a particular training, we defined the number of samples that we want, and based on the, like Bhaskar and Amit already said, there are already like predefined functions in the library that are there. So we just put these parameters that we choose, and we create one quantum instance, and then eventually we can train a model. So based on that, we calculated the loss function for both generator. In the first figure that you can see, there's this generator loss function and the discriminator loss function. So basically, what discriminator trying to do? Discriminator is trying to maximize its loss function. On the other hand, generator is trying to minimize the loss function. So eventually, after 3,000 iterations, the both of them reached some convergence. If we like increase the number of iterations, the model will definitely improve, but based on the time constraint that we had, so we continued till 3,000 iterations, and we saw these kind of scenarios which eventually like satisfies the theory behind. And Similar case was with entropy. So we calculate entropy by one formula, which is like the ratio, basically the ratio between generated and the real one. So it like there uh, the data which is getting generated should like more likely like the real data. So they eventually the relative entropy decreased, and the last one that we can see is the distribution. One is actual normal and one that we got from our study. So it was almost like imitating the distribution that we provided as the training set. So this is what we have observed. So we have like implemented for one particular type of Q-Gan that we can see, but we can like basically what we can explore as many combinations from this from the data type or discriminator type or generator type that we can see. We can see different scenarios we can run, and then we can like see the results and check like how things are getting better in which scenario, and we can explore that way. So we are in that phase. uh, this was for one of the types that we explored. So yeah, this was what was what we did in the QGAN implementation part. So yeah, Bhaskar,
Yeah,
over to you.
great,
Thanks.
great. Thank you, Anirudh and Amit. So I think, yeah, that's pretty much like what we wanted to show. So it was the entire presentation is all about what we explored and what we tried implementing, and like and what we understood or learned. So like as a conclusion, what I would say is like anyway, like we would definitely have a discussion. Any questions can be raised, and we can also try solving them. We would also like to hear about any experiences of someone like who implemented any of these kind of algorithms, and in a practical sense or any sense. And also we would also like to understand like if there are any suggestions about what else we can do to improve, or what else what in which direction which we can go in our research. So these things we would be like very excited to listen to. But over to you, Mert. So like you can take this forward, the discussion, the questions and everything. Yeah.
Okay. We have, thank you everyone. We have maybe like 10, 15 minutes for questions. Also, Yosh, do you want to introduce yourself? Because we kind of missed you in the first part.
Right. Hi everyone, I'm Yosh. I'm a third year at Stanford studying math and physics, potentially computer science in the future. And yeah, I'm just really interested in quantum algorithms, specifically like quantum computational complexity. And yeah, thanks.
So do we have any questions? We can open the floor for discussion.
Maybe I will ask you guys a question.
Yes.
Can you hear me?
Yes, Alex.
Awesome. So, I mean, this is a great exploration, right? It's very interesting to see kind of outside view on the Q network and kind of what's its advantages and disadvantages. So, I would say, what do you guys find as a Sigmoid, as a third party using this network? What do you see here as an opportunity right? And for you as a company, and how can IBM Q Network help you kind of achieve it better, right? So given that you've done these experiments, what's your feedback essentially? And like in your roadmap for quantum exploration, where do you see quantum business going? How can we help you get there?
Thank you, Alexei. Thank you for that. Sounded more like an offer as well as a question. But frankly, we are learners in this space. Uh, Analytics and data science is a very competitive space, right? And being ahead of the curve with vis-a-vis other companies and being able to implement or being able to identify solutions or techniques which can help us remain ahead of the competition, that is what we are thinking right now. And for that, this is our experimentation start. We want to ramp up on this. uh, Thankfully, as in from your side, we saw interest, and that gives us more enthusiasm to keep on working on this. We had sort of put some brakes on it. Now we feel that yes, we are going to work on this with some more funding internally as well as externally, possibly. From our side, as in see, most of the problems that we see from our clients are real business problems, and for those, companies are still struggling or resorting to the traditional methodologies and algorithms to work on it. As soon as this speed up comes in, and with real time analysis becoming more popular, the data growing very fast, anything which helps us uh, make or run algorithms at a very fast pace, I think that's going to be something that we would want to learn. We want to ramp up on that very fast. We had already mentioned that with D-Wave, we were not able to explore anything further. With IBM-Q, we were able to explore a lot. It's a good starting point for us. We want to ramp up on this and to expand our R&D capabilities as well. Machines is one from a hardware point of view, a space wherein we can explore these algorithms and make them applicable in real business applications. That's the space wherein we would certainly be looking forward to any help. I think having it open source, having it available for public to execute, I think that's one of the already good initiatives from IBMQ. We would want to enjoy the benefits of it in future as well.
Awesome, thank you. Thank you. And I think for experimentation, sorry, I have a train here. For experimentation with higher number qubits, we have partnerships, so we can talk about it separately, because there are much higher number qubits, and I think for kind of interesting tests, it will be interesting to try what you guys did at higher number of qubits. So
great. So I think John has a question, right?
Who, me?
John?
Yes. I just put an article up there I found in physics, APS physics, about superconducting qubit that protects itself. So that seems to be on the hardware level, where everybody's heading. You're in the algorithm level. So what's the repeatability of your experiments? I mean, do you have a consistent error correction, or does that slip between the certain boundaries, and then the error correction itself is not totally stable yet to prove that the error correction really is error correction? You know what I mean? It's not that the results shift, it's the actual error correction is actually more accurate, because that seems to be what everybody's discussing, is how close in the error correction can we get to prove that the error correction works. That's all I keep seeing. I mean, maybe it's me, but that's all I keep seeing when I did electronics. That was the whole thing, the accuracy of how things were going wrong and how you had to trace things as a procedure. So each time you did it, you had 12 parts in here, which one was actually doing it and why was it doing it? And the idea is that you can replace all the parts. Okay, well, big deal. You haven't proved anything. It's just the idea, can you get down to that one part that's actually got a hiccup in it because there was a malfunction in the manufacturing of the chip we bought. So you understood that the chips were actually cheap, and we should go to a higher grade chips, and we'll eliminate that entire problem because it gets in the engineering production phase. That's from like 10,000 years ago. So I think it's still relevant. But it just dawned on me, I just keep looking at everybody's talking about everything, you know, so that's something to focus on. Like this article I just found on superconducting qubits that protect itself seem to be getting the qubit itself in a position where it's actually corrected and it's stable. So no other influences can actually throw it off. So we have a better view of what's going on as we target, you know, getting an accurate assessment of how these things can go to 1 million qubits or 10 million qubits or whatever, because it's 16, you said 16 million or 16 qubits, right? Which is really sophisticated at this point for what you guys are doing. And it's like, you know, I applaud that. Yeah. You know, and go with that. But the idea is the next stage is they're trying to get to that level. I'm just saying, this is some information maybe can help you out.
Certainly this helps.
Yeah.
This would certainly help us further our research, but frankly, that question was way above my pay grade to answer.
It's just something as I'm kind of learning how this works. I'm just there are things that stick out, like this parachute. I spotted this, but somebody else figured this out when it came down. I'm going like, there's got to be some reference out there. And all of a sudden I find out that somebody in school who's much younger than I am and sharper and more, you know, more hungry, found this out and figured out what they put in that message. Okay. So there's those little things that when you get that little bit of excitement there, you just want to kind of follow it, which is what you guys are doing. You know, you have a lot of excitement for this. I mean, you really, really want this to work. And you really, really seem to be putting the time into making sure that what you're doing is accurate. So it justifies the work you're putting in there. And even if you come to a conclusion where, oops, it isn't. Well, how do you do that? It's a stop. But the next stage is incrementing more and more accurate correction in order to get where you need to go. So I applaud that. Yeah. Yeah.
We are trying. We don't understand everything. We don't understand the technicalities a lot as well. We are trying to work our way and be able to understand that. But
sure.
Thank you. We'll look into it. It will certainly help us enhance our knowledge as well. But Anil, do you want to say something?
Yeah, I can like answer some part of it. So as John said, like so for this quantum computing, for it to be in action, so we need this qubit in action. So eventually if we like, there is some like external magnetic field that we provide for changing the direction of electron, which is like it will tend to be in the like the natural state or the low energy state. So if we want to change the direction, we'll have to provide certain external field for it. So for maintaining that, all the like, I think that there is some research going on, like how can we maintain it better. Otherwise, there is one phenomena with this qubit that's called decoherence, where a qubit loses its like power or what, like the properties basically on which it's acting. So yep. So I saw that article. So it basically says the title itself is a superconducting qubit that protects itself. So it's basically, I think I will go through the this article and I'll figure it out. But mostly I think mostly the fight is going on, like how to achieve that state and how to keep that electron like for maximum time that we can.
Right. I found that when I was doing doing electronics, we had problems, like I said, with the chip. We bought the wrong chips. We needed to go to a higher price chip, but they were trying to buy them in bulk. So the problem was we were having issues. And it came down to looking at how these things are actually, the lithography works, and you get into the superstructure of the chip. Because every time an electron goes through a passage in a hole, it's going to leave some kind of trail, and it's going to bounce into something in the lattice structure. I had better books than I have today, but some really detailed books that basically showed lattice structures, designs that basically, as you see, the electron could bounce through it. As it bounces, it vibrates, and that vibration turns into heat. And the more that happens, the faster you go, which is why the cooling process is, because it holds that more rigid. So as it hits it, it's resilient as opposed to flying out and burning up. So when you see your chips burn up on your computer, your processor at one point, remember overclocking? You know, when overclocking wasn't a big thing, you know, the gamers went out there and wanted to overclock these processors, and they basically were burning them out. And they brought this to the manufacturers, and they said, hey, we want to play these games faster than this. How do we do this? Well, then it gets down to clock speeds and crystals on the board, and then they just had to basically process the material so it could actually handle the overclocking. So now overclocking is just not, it's not even mentioned anymore. It's mentioned as a fact it's a short-term goal for a higher level operation because they've already put it in the manufacturing process. So that's kind of all I was that's where I was looking at things.
Great.
Hello. Yeah, I just have a couple of questions. So first, I think Bhaskar had given about implementation of QML algorithms, right? Probably QSVM or something. I mean, does running QML algorithms give any validating advantage, quantum advantage, other than runtime? And if not, then what are the challenges that that are required? And I mean for that, that are to be met actually.
Yeah. So as far as the entire quantum space is known, so runtime is the biggest advantage we get for any of the quantum machine learning algorithms, or like any quantum algorithm, except for maybe like as he was talking about the cryptocurrency or like encryption or decryption parts. Like there we have an additional advantage of not just time, but also the uncertainty as well. But like when it comes to the quantum machine learning type of algorithms or any classical algorithms in a quantum state, I see the time advantage is the only huge win. Yeah, and like other challenges are like we have to create a lot of libraries around it and convert build a lot of circuits converting the data and build hardware. So a lot of challenges around it, but that's what I feel. Ashish, anything additional to add to this?
No, at this point of time, as in from whatever we have been able to run, we have not been able to identify any advantage so far. But that is not because the quantum theory doesn't work, but that is more because of the current challenges of the way we are dealing with data. We are still dealing with data in the classical sense, right? Tabular, columnar, worst case scenario in a big data format, but that's where it is. I think the data part needs to align well to be able to run any QML algorithms. So advantages will come, but so far, as in we have not seen that it performs worse than the classical algorithms.
Well, I mean, across all industry. Sorry, go ahead, Kran. I don't want to interrupt you.
Right. Theoretically, it should perform better. Yeah, but practically it is not. It's just that like we also do not have great machines, like maybe having better machines or having better built machines also, that drastically would change the game. Anyway, yeah, Mert, you were saying something.
Yeah, so like across industry, I think there are two cases of quantum advantage, proven quantum advantage, and one is Google, and the other one is photonic advantage from China. And they're not useful at all. They're just toy problems. So it is kind of naive to expect advantage right now. I mean, optimistic, not naive. I expect it. I mean, tomorrow I wake up and when I do my research, I expect to see advantage on my computer. But realistically, the quantum advantage on a useful problem is likely to happen. Not tomorrow, but soon. And it's not gonna like be an exponential speed up probably. It's like we'll see small advantages through hybrid algorithms where most of the work is done by classical devices, and that small quantum component is doing the thing it's optimized to do for. And this brings us back to Kevin's earlier question on not on the hardware side, but on the application side, where do we expect to see advantage? And I think it's a good question for everyone. So if everyone can like write their thoughts on like their guess on it on the chat, I think it would be a great opportunity for us to share. So the question is, where do we think that? Sorry, yeah, go ahead.
Yeah. I guess there's some work going on. Like, I think there's some published work going on in quantum teleportation, right? I mean, maybe does that have any relation with the quantum supremacy or quantum advantage that we're talking about? I mean, or that is something completely different.
Sorry, I couldn't hear the last question.
Yeah, so there's some work going on in like I think quantum teleportation, and I think so does that have any relation with the quantum advantage that we are talking about? Quantum teleportation. Recently.
I'm not sure what you're referring to. So if but I mean, all the work being done in this space is kind of related to quantum advantages, like driving research forward. So yeah, I wrote my answer. For me, it was random number generators, real random number generators. That's my thought. That's I think related to what Ashish was talking about in crypto and security.
Okay. Yeah.
But yeah,
I just have sorry to interrupt you. Like I just have one more question to I think Anirudh. Like I mean, can you please like overall, like on a broader spectrum, like what are the objectives of Q-Gan actually? Like what are we wanting to achieve actually? Can you please give that?
Like the main objective is to generate the data which resembles. So it basically what it will do, it can improve whatever I have, or like if I should say so basically the training data set that I'm providing, so it follows some distribution, right? So what my model is trying to do, it will try to estimate some density, and it will the generator what the generator will do, it will like other than those samples, it will try to generate more data from the same distribution. So eventually my model will train for better. So that is the idea behind creating it. And other than this, the GANs can be used for enhancing, like in the image side, like if you work on that, it can enhance, it can boost the features of some image. Or I have also seen this implementation of GAN where if you simply provide one sketch, it will colorize it, or like it can generate some artworks which are not there and which are like very good. Like since the GANs are developed, since the starting of GANs, like they have developed very much, so people are actually using it. So the site which I said, no, that person does not exist.com, visit that one and see that image and try to guess whether that image is real or not. That image is result of this one of the GANs. So it has
I'd like to add one more point, that we can use the GAN to generate the data in the quantum format. So we can use it for the algorithms, or we can, as Anirudh said, that we are able to we are trying to generate the data set which resembles some of the distributions. Like here in this case, he has generated the data which resembles log normal distribution, right? So we can generate some of the data which we want to train or classify, as in case of quantum superconductor machine. So we are using a classical data and then converting it to the quantum data. So in place of that, we can directly use the Q-Gan to generate the data which resembles the classical data that we are using to classify, and we can further use it to give it input in the quantum circuit for quantum superconductor machine.
Okay. Yeah. Thank you.
Yeah. Okay. I think we can start wrapping up. Also, when I said there were two proven quantum advantages, there's also one paper that came out last week. So it's not I wouldn't call it a proven quantum advantage, but it's a good good supporting paper for annealing advantage. So D-Wave just published last week, and I'm gonna put it on the chat. You should check it out if you're interested. They claim annealing advantage for this very good classical method, but it's not comprehensive against all classical methods. But it's an empirical result. That's interesting. Okay, so thank you everyone. We will publish this video on our website, which is quantum.sv. I'll also put that on the chat. Thank you all for coming. Thanks to Sigmoid for taking the time for this very well-prepared talk. We hope to see you all again next month, the last Thursday of next month. Is that right, Alexei?
Yeah, that sounds good. Sounds like a plan. Thank you very much, guys. It's everybody.
Thank you.
Looking forward.
Thank you.
Thanks to
Pleasure.
everybody.
Thank you, everyone.
Bye-bye.
Thank you for providing us
Bye-bye.
with this. Bye.